In this video, what I want to do is derive the equations of motion of the system that we see here. And what this system is, it's two blocks. One block has a mass m1, the other has a mass m2, and this block that has a mass m2 is being pulled to the right with a force of F. Now, blocks m1 and m2 are connected together through a damper and a spring, and m1 is also connected to the wall with another damper and another spring. So they all have their damping constants and their spring constants, C1K1 and C2K2. Now, the assumption we're going to make is when there is no force and the system's at equilibrium, that the springs are initially unstretched. And we need to figure out, what do we do with this damping force? So if we look at this damping force and we look at a simple example, so we're just going to have a block, and let's say the block's going to be moving to the right and we have a damper on it. And I don't know, it's connected to a wall. Well, we're moving with some velocity to the right. This damping force, let's say, has a coefficient of c. The damping force is going to oppose our velocity. And this damping force right here is going to be equal to c, this coefficient, times whatever our velocity is. So just like our spring constant has a force of kx, the damping force has a force of cv, where v is the velocity. And we're going to use that in this problem. Now, when we're making the assumptions and we have two masses, it's very important, just like when we were dealing with springs, that we keep our assumptions constant when we're dealing with each of these masses. So what we're going to do is we are going to draw a free body diagram for both of these masses. And the majority of this free body diagram is very easy, since it doesn't change whether mass 1 is moving farther than mass 2 or faster than mass 2, right? Everything here is going to stay the same. This force right here is going to stay the same. We just need to figure out what's happening in the middle. So let's take care of this force. We'll take care of this force first. So this force F is always going to be applied force to the right. This, well, we're told that we're moving to the right, and that means my velocity right here is going to be moving this way. So this C1 is going to oppose that motion. So this is going to be equal to C1 times, we're going to say this is x1 dot, so its velocity. And this spring right here, well, if we're stretching the spring, we're moving this way, we're stretching the spring is going to want to have a restoring force, and it's going to try to get the spring back to its natural position, its unstretched position, and that force is going to be K1x. So those don't change, and those make it very easy. Now, what's happening in the middle, we're going to make some assumptions, and this is how I work these type of problems. I make the assumption based off whatever I consider my leading block. I like the block that is having the force applied to it, or whatever it is. So I want to say that x, the velocity of this block, is going to be greater than x1. So these can both be moving just like the spring, but it's going to be that relative velocity. So what that means is this relative velocity, this is going to be moving faster than m1, and we're going to say it moves farther than m1. So that means with my damping force that I'm moving in this direction, and my damping force is going to oppose it. So this is going to be C2, and it's actually going to be the relative velocity. So x2, the velocity of x2, minus x dot 1. Let me put it like that. Now we have an equal and opposite force going this way. And what happens with this spring down here? Well, the spring, this is moving farther. This is going to stretch, and it's going to want to pull back this way again. We have the opposite force that goes like this, and we're going to have K2 times X2 minus X1. And this is our free body diagram. It just gets a little tricky sometimes when you're dealing with these relative motions between the same block. But again, what I always do, I pick one, I make it do what I want it to do. And for me, this M2 was easier to see, and then I can figure out what's happening. If you had assumed that M1 was moving faster, your arrows would be switched around. These two terms would get switched around, but you'd get the same answer. So it's a good exercise to try. All right, so now that we've done our assumptions and we've done our free body diagram, we want to work through our equations of motion. Well, our equation of motion is going to be the sum of my forces is going to be mass times acceleration. I'm going to write this for each of my blocks. I'm going to start with block 1. So we're going to say in both cases that right is going to be positive. And I'm going to reverse the equation just right now. So I'm going to have m1. I'm going to write my acceleration as x1 double dot. And now this is going to be equal to minus c1 x1 dot, so that velocity, minus k1x. And now that's these two forces right here. So now I have to work with these two forces. So that's going to be plus c2. I'm going to multiply this out right now. x2 dot minus c2 x1 dot. Let me just give myself some room. I just need some room to write the rest of this equation. So then plus k2 x2 minus k2 x1. So now I want to just go ahead and rearrange this. I want to bring all my x1s to the other side. So I'll have m1 x1 double dot plus c1 x1 dot. This is plus k1. I forgot a 1 right here, but x1. 2 is going to stay on the other side. Plus c2 x1 dot plus k2 x1 is going to be equal to c2 x2 dot plus k2 x2. I can do one more thing. I can just sort of combine my coefficients. So I'll have m1 x1 double dot plus c1 plus c2 x1 dot plus k1 plus k2 x1 is equal to what this other side is, c2 x2 dot plus k2 x2. And this is my equation of motion for my block M1. So now let's do the same thing for block M2. So again, we're just going to have M2 x2 double dot is equal to, well, now we're going to have minus c2 x2 dot plus c2 x1 dot. Because I'm just combining this term out. This is going to be, right, this is a minus c2, and I distribute that term. So we're going to do the same thing here. So minus k2 x2 plus k2 x1. That's this force. And then we're going to have plus f. Okay. Now let's bring all my x2 double dots to this side. We're going to have m2 x2 double dot plus c2 x2 dot plus k2 x2 is equal to c2 x1 dot plus k2x1 plus f. And this is my equation of motion for my second block. So hopefully this video has shown you how you can apply this damping force to a free body diagram and to a system and come up with an equation of motion. Now, just remember this damping force right here is always going to oppose that relative motion that you have.